Okay, good morning, everyone. This is the second lecture of the forward inverse modeling, as I said, but I'd be glad to go through whatever we have covered so far to make sure everything is crystal clear to all of you. And then we will start to cover new material for the course of today. That's the schedule of the course I have already mentioned before. We started the course last week. We went through incompressible flow, elliptic problems, and then you had a practical session where you developed a 1D incompressible flow simulator with Python. And now this is the class of today where we are going to cover the 2D systems. Before we go to 2D, I'd like to review the material for the past lectures, and then we will follow on to the 2D session, because if also we are reminded about whatever we have done so far, the development of the 2D would be also a lot more convenient. Just a reminder, your first homework project submission is due 27th, so you don't have more than about 8 days left. The class covers explanation of what and why we use reservoirs, reservoir simulators. What are they and how can they help us in a geoscience field? And then we develop our flow simulator. Flow and pressure are interchangeably being used. So when I say flow simulator, I mean also pressure simulator. And then we move on to transport, which mainly covers saturation transport, immiscible flows. And then we analyze the consistency, stability, order of approximation of the code. We will just discuss that also partly today as well. This is part of the new material I'm going to cover today. And then we couple flow and transport. We call this IMPES, implicit pressure, explicit saturation. These are going to be a lot clear as we go through the course. Development would mean that you need to do some analysis, discretization, location of the unknowns, everything in the paper, implement it in your Python code. And then when you get the results, please remember you need to analyze, interpret, what do we mean by what do we learn by these results as well. You could conveniently solve something like this, a heterogeneous reservoir. This is a test case which is established in the literature quite well. It's called SPE10. Then you can inject a new phase in here by the end of the course and then see the evolution of the second phase into this reservoir. In fact, that was one of the exam questions that I asked 2 years ago from students to download the properties of this reservoir from literature. I gave the address of where these data sets are being stored, and I asked them to analyze and simulate this problem. So in the class, they had to go and download the properties and then run it, make adjustments with the codes, and then make these runs and report it in the final report of the exam. So they had about 2 hours or so to do this. So moving forward, there are 3 projects again. Scientific reports would be needed for each of them. And the scientific report would cover title, your name, abstract, a paragraph, what did you really do, what did you learn, introduction, methodology, results, discussion, references, appendices. They don't have to be extensive. They can be 5 pages, they can be 8 pages, but not really lengthy, please. And exam will also take place if you have passed the 3 projects, which is you have received more than 50% for each of them. And that would be a template of the previous year's reports. See, there is a title, for example, 2D. This is for 2D two-phase flow systems. That's Alex, who did that long ago. And this is the abstract. You see, this doesn't have to be really lengthy. An introduction also, and then you have governing equations, very brief review of what the governing equation is. And for example, his report was 10 pages, or the other one as well. Susanna submitted this, and her report was only covering 7 pages. So you don't really go for beyond those, but see how neat, how structured, how easy it is to read, to understand, and to learn from these reports. Please don't hesitate to do this, and instead of spending a lot of time to make it 50 pages of report, just make it 7, but very neat, dense, and you can always make references to the course. That course that I was offering that year was called Reservoir Simulation. And you see, you can simply just refer to the course material if necessary in order to save a lot of stuff. Yeah. So with that, we move forward to the flow problem, to a simulation of the flow, pressure and velocity. First, we explain the reservoir simulation concept, and then we develop our simulator, okay? So the first step that we covered last week was about what understanding what a simulator really is before we go forward with the philosophy of why do we need it and how it can help us. And we covered this fact that the reservoir simulator is a toolbox, is a scientific approach to quantify the process, understand what happens, be able to manage the process, be able to engineer the process through the controllable variables that we have. If we can place the wells, if we can change their property of the injection production, or we can also alter the property of the reservoir sometimes as well. So reservoir simulator in brief as a toolbox is a piece of program that makes the machine, the computer, do some actions and then allows us to do some analysis with those actions. The input to this toolbox are geological data, experimental properties, constitutive laws. These are the input data. How are your phases behaving? What are the functions that you have to describe their properties, like permeability, relative permeability, viscosity? Is viscosity a function of pressure or not? Geological data would give you the structure of the reservoir, the properties, the population of the properties. Many times we use geostatistical sciences to populate the properties. With these data sets, your reservoir simulator would do some actions, would discretize, solve the problem, solve PDEs, sets of PDEs, partial differential equations for flow, transport, energy, depending on the process that you have. And then it applies, you make the machine do this, proper simplifications for the physics and geometry. If you don't have heat transfer, you just neglect the energy balance equation, obviously. If you have single phase flow, there would be no transport, it would be more flow, unless you have concentration also there, like polymers or some tracers. And then you apply initial boundary conditions and location of the wells, configurations of them, and then that problem becomes well posed. After that, you can solve with some given situations. You can analyze, understand what the output would be. For example, this is the transport of some species. You can see them, and then you start to analyze your productivity, your stress field, heat transfer, how much heat are you producing from this reservoir, and what are the sensitive parameters for you. At the end, it would allow you also change the controllable parameters and manage the resource or optimize your profit overall objective. Is it productivity? Is it safety analysis? Whatever it is. So it's a toolbox that allows you have a lot of control on the input parameters, understand what will happen in the output, and be able to manage and control the system. So that's what many of you would just be able to mainly guess. The important part of this business here is that scientific approaches in the history of human being has covered analytical approach. Many times the mathematicians were quite they contributed significantly to allow us solve PDEs. Experimental sciences have contributed extremely as well. We observe processes, we try to analyze them, we try to see what if we change the input, if we change flow rate, if we change this and that, what would be the output. So experimental approaches are also one pillar of scientific experiences. And numerical approaches, machineries, machine computers as well. So when computers were invented and were used by engineers, they allowed a lot of possibilities for calculations, for computations. You solve the same PDEs, but you did not have to neglect a lot of physics that you had to do for analytical approach. Now with numerical approaches, you can have full physics involved because computers can help you with solving the long, excessive, big, massive linear systems if you would allow for all these kind of physics to be involved and a lot of grid cells and so on. So these are approaches, scientific approaches we've had as engineers: analytical, experimental, and numerical is the subject of the course. We also covered last time that apart from these three, machine learning, artificial intelligence is becoming the fourth approach, which is data-based or experience-based, network-based, predictive approaches or quantitative approaches for prediction of a system behavior. And that's why I have put 3 dots in front of the numerical one as well. Now, one very, very important thing I would like to make you aware of and remind you about is that reservoir simulators in geosciences are different than simulators for aerospace engineering or for other disciplines. Here, no matter what we do with the most advanced ways of data collection, characterization, geophysics, geology, and so on, our understanding of the subsurface remains largely uncertain. And that means your input parameters are your best guess. They are not perfect. So your output would be your best predictions, but they are never fully predictive. Then the challenge here becomes clear to all that then why do we do simulation then? If the input parameters are so uncertain, why do we do this simulation? This is the discussion that we had last time, that we spoke that about the fact that we would like to simulate for not just one realization, but for many possibilities and find what are the possibilities of the outcome. Through data collection, time-dependent live data collection, we can narrow down our uncertainty. And also, I would like not just to use the simulator to give me for one input, one output, but also to understand what are my sensitive parameters and how uncertain my quantifications are. So I rather go for acceptable solutions to possible realizations, many realizations, instead of going for exact solution for one specific problem, which most probably is going to be wrong because our input parameters are always uncertain. And it's very important to notice that we will use this quantitative toolbox to do sensitivity analysis, change our parameters, and see which parameters are most impactful for the outcome to understand the sensitivity of this black box instead of focusing too much on one realization. Although we would also get results for one realization, but that's not the scope here. We would like to change parameters, to change physics of the flow, rock properties, and all the uncertain parameters that we have, or sometimes being curious to say, if we would have injected with higher rates, would the production be something as I would expect, or there will be some other physics happening? Would I, for example, crack my rock if I would have increased the injection rate and have changed the stress field, for example? So remember that reservoir simulators are not just something for fabricated material here. They are for natural processes. Our input parameters are always uncertain. So we use simulation to make results or solve PDEs for one realization and for many, many, many realizations. And we get a range of uncertainties. And through data acquisition, we will narrow down our uncertain range. And instead of single realization-based approaches, we would do many realizations in order to understand sensitivity of our system and quantify our uncertainty. Now let's move on to flow simulator. First, we formulate flow, Then we discuss about the challenges, and then we discretize, analyze it, and we develop our simulator. Again, the deadline for submission would be 27th of November. Let's formulate the flow. You have seen these slides before, so I'm going to be very quick so that you remember what happened so far. We have a variety of scales to discuss, study, and make simulation for. The study that we do in this class is actually about this part from continuum scale on, which means the continuum scale would be where we have Darcy's law, where we have a Darcy's scale. And as such, we would like to be able to describe our problem, to describe our system at the Darcy scale. That Darcy scale system requires input parameters from other scales. From this scale on, from the lower scales, it requires input parameters in order to be well described. What are those parameters and functions? You're going to learn about them in the physics course. We have started the physics course already, so you know that from pore scale to continuum scale above, we are going to get permeability, we are going to get fluid physics of relative permeability, capillary pressure. These will be more known to you as we proceed in the course. The main scope here is that I'll be able to write Darcy's law, and I'm able to get the parameters I want from the higher resolution physics, either experimental based or numerical based. And these graphs that you see here, they are CT scan of injection of CO2 in a piece of rock. So either experimental or numerical, I'll be able to get the parameters that I would like in order to describe my system at the continuum Darcy scale. So let's move on and do this. Looking at the nature we discussed yesterday, when we look into the nature and we would like to describe it with mathematics, the powerful tools that we have as engineers are conservation laws, which means we know that mass, momentum, energy are conserved. Depending on the process that we have, we use either of them. In continuum scale for porous media science, we use many times Darcy's law instead of momentum balance. If I wanted to do porous scale, I wouldn't do Darcy. I would do Navier-Stokes or a Stokes flow. But here at the continuum scale, I'll be using Darcy's law. Of course, I need then also constitutive relationships from physics laboratories, from physics theoretical physics, understand density, viscosity, equation of a state, how thermodynamics also would hold given the pressure, temperature, how would my phases distribute each other to liquid phase, vapor phase. Physics course will cover all of these, So you just need to stay patient with the physics course and go through the lectures there. Here we allow you be able to solve them numerically in this course. Okay. So let's review mass conservation for phase alpha per unit fixed volume as shown here in this box. The conservation says change over time of the intensive quantity of mass, which is mass per unit volume that I have, plus net outgoing flux of my phase alpha is equal to the source terms if I am injecting or not. Intensive mass of alpha, intensive conserved quantity here, which is per volume, would be porosity, which is if I have a box, phi part of it is void. Within that phi part which is void, I have density, rho alpha, and then I have volumetric fraction of phase alpha. If I have a porous material, and for example, these are rocks, the white space now will be filled, for example, by two phases. 20% by phase alpha, like CO2, 80% by brine. these phases would fill the empty gap. Their summation of volumetric fraction would be 1. We are going to learn about these a lot more in details in the physics course. Here, it's only mainly we are focusing on solutions to these problems rather than understanding the physics behind them. Now, you know that from Darcy's law, velocity for each phase is the mobility of that phase gradient of pressure. Mobility would be permeability, relative permeability, and viscosity. If it is single phase, we have covered it already. Single phase flow would say that the Darcy's law would be minus K over mu grad P. And this is exactly what we are studying in the physics course. So this is just mainly to expose you to more complex scenarios. With these parameters that we just described, I can fit my M here, I can put my U here, and I will reach to this conservation law. Change over time of mass, intensive mass of my phase alpha, plus the net outgoing flux of it is source term. That's the governing equations. I could have started from this equation, by the way, because this is more mathematical and simulation course, but it would be nice to just know what it really stands. Now I would like to take this equation and say that's my mass conservation. I would like to assume it's incompressible. So Barbara, if a system is incompressible, what can I say about the density?
It stays the same.
Exactly, precisely, thanks. It stays constant. So density will be constant, so I can just delete it like this. I can cancel it out. I can divide by density, which is constant. At the same time, incompressible fluid and also rock as well. So porosity can come out because it becomes also constant. So I will end up with phi ds alpha dt minus divergence rho alpha grad P becomes Q alpha. Now, if I write it for phase alpha and for phase beta, for all phases, and make a summation operator on them, I will do this summation for all of them. So then I will introduce summation inside my system. So it will be summation of phi ds alpha dt minus summation of divergence lambda alpha grad P equals summation of Q alpha. Summation of Q alpha, I call it Q, total source term. Summation can go inside. That becomes divergence of summation of lambda alpha, I call it lambda, which is total lambda, total mobility, grad P. And summation, when it goes inside, it becomes phi d dt of summation of all volumetric fractions of saturations. And I know that all fluids fill the pore space. So summation of the volumetric fraction of each phase at the end would be equal to, Beer, would you say so? What would be the summation of all saturations?
1.
1, fantastic, thank you. So that will be 1. So change over time of 1 would be 0. So this term totally goes out of the system. At the end, my incompressible pressure equation will be minus divergence lambda grad P becomes Q. And this is the pressure equation that would hold also if I would have assumed single phase flow, steady state. Now with even multi-phase flow, when I write total balance equation with incompressible assumption, total balance equation with incompressible, I get this pressure equation. And when we go towards next week, end of next week, or maybe the week after, I'll explain to you why do we derive pressure equation? Why aren't we going to directly solve this equation for pressure and saturation directly? Why do we bother with all these mathematics to get a pressure equation? There is a reason behind what all these processes are being done. And it just needs to be taken a little bit of time until we go to coupling processes and see how the system behaves if you decouple pressure and saturation, or you would couple them together. So this will come in due time. So that's my pressure equation that I have, and I can simply start to develop a simulator to solve that problem. That's exactly what I did. So I am making incompressible assumption, then I apply a summation operator, and then I write my equation for total balance equation for incompressible flow becomes this pressure equation. And we discussed last time that this pressure equation is elliptic. And it is global, meaning that each point would impact everywhere else in the system, and it will be impacted by everywhere else in the system. If you change mobility of your reservoir, this is your reservoir, and you have incompressible fluid there. If you change mobility here, the pressure distribution would change everywhere immediately. There is also no time here. There is no ddt here. So that's ellipticity. There is no time in here, change of lambda. So if you crack the rock here, you would change pressure everywhere. If you have a shared reservoir with your neighbor, you start to change something in your side, produce a little bit more out of your contract with them, they will immediately understand you have done some changes in the system. Because the system is elliptic, it doesn't have time dependency in the system. That's the meaning of ellipticity. If I open the window, I immediately freeze, then I am elliptic. If immediately something changes and I feel all the system everywhere would change immediately with no time. Yeah. If I would have added compressibility, I would have observed parabolic pressure equation. They come next quarter. The challenge then becomes the fact that I need to solve for pressure for everywhere in my system. I cannot localize the pressure equation easily because it's a global problem. I should solve it. And if I have a system which is kilometer scale, I need to solve for all points of my system to understand what is the pressure distribution everywhere. If I have a special permeability somewhere, that would also impact everywhere else the pressure. So pressure equation is one of the most expensive part of any simulator because it's global. It is global. You need to solve big systems for it. So let's develop discretization schemes for it. We have covered it already quite many times. We go with incompressible conservation, which is divergence of velocity, is Q, is source term. If you do not have source term, divergence velocity would be 0, meaning that whatever comes should go. There is no net outflux in the system. Darcy's law says velocity is proportional to some factor lambda, whatever it is, it's physics would tell us, times gradient of pressure. Now, if you combine the two equations together, this one and this one, you put velocity here, you would get this pressure equation that we just described. And I would like to develop a simulator for this. So let's start to focus on 1D system. 1D Cartesian system says d nabla, this guy becomes ddx. This becomes ddx. Divergence and grad become ddx. So ddx lambda dp dx is q, and I would like to solve this problem. I would like to solve for my pressure. I have a reservoir, 1D reservoir. Left, for example, face is P right, P left. The right one is, for example, P right. And I would like to know what is my pressure distribution here. When I know my pressure, I can solve my velocity afterwards. When I know my pressure, I can say my velocity is minus lambda grad B, which is, in this case, minus lambda dp dx. So I apply gradient operator, I find the dp dx, multiply by lambda, I find my velocity. So let's focus on dp, solving the pressure equation. And this is exactly what we have done before, to say, let's select what scheme do we want to use. There are two options that we cover in this course. One is finite volume, another finite difference, staggered grids, to keep it conservative. These are locally conservative schemes. Let's start with finite difference, which is more convenient now. Then also we cover finite volume as well. How do we do that with finite difference? We have already the pressure equation up in here, and we know that for single phase flow, the lambda factor there is permeability divided by viscosity. So I have a one-dimensional reservoir, and I have discretized it, made it into pieces. From left to right, I have made just n cells in it. Cells are delta x apart. For the first and the last cell, I know that my boundary is delta x half apart from my centers. All others are delta x apart. P left and P right could be given to me too. There could be also, I have none of them known, but I have wells in the system, but there could be that P left and P right pressure at the left and right boundaries are also given to me. I place my unknowns. Now here comes the sensitive part. If we place our pressure at the centers, which is the case that we are doing here, so P0 is here, P1, P2, all the way to Pn minus 1, because I have n cells. My velocities, we discussed that before, yes, last week, that need to be at the interfaces. That's the meaning of staggered grid. Velocities should be at the interfaces because if I have a velocity here, whatever leaves cell 0 should enter cell 1. If I place my velocity at the interface, I'll make sure that whatever leaves cell 0 would precisely enter cell 1. Right neighbor of right interface of 0th cell would be equal to the left properties, left interface of cell 1. And so all velocities would be like that. That would ensure mass conservation locally. That would ensure mass conservation locally. And so with these values, and by the way, whenever I do P bracket 0 or U velocity bracket 0, 1, 2, 3, it means I am writing it in Python terminology so that your codes and your notes become almost the same. So this is the 0th interface here, which is left interface. Then it is first interface 1, interface 2, interface 3. I will have one interface more than the grid cells, naturally. Now with these, I'd like to model my system and discretize it. I know cell I has property lambda I, cell I plus 1 has property lambda I plus 1, I minus 1 has this property. Grid spaces are equal delta x for them. And I know that I have put my velocities also at the interfaces. The green one is the incoming flux, the red one is the outgoing flux. Now I would like to start discretizing the system for cell I. For cell I like to start from this governing equation and get rid of the first derivative term. Whenever you have divergence of flux equals Q, you first say divergence is what? Is net outgoing, meaning that I need to say the flux outgoing at I plus half. This is the green, this is the red one. The flux at the right interface minus the flux at the left interface divided by the distance between left and right interface becomes Qi. This is the distance between I minus half to I plus half interval. So that's the size of your simply grid cell. And that's why it is delta X also for the first and for the last cell, because the right and left interfaces of the first and the last cells are also with delta X apart from each other. Now I need to know how would I calculate lambda at I plus 1 and lambda at I minus half, I'm sorry, lambda at I plus half and minus half? This is something I need to know. And also I need to know how would I calculate dp dx at I plus half and at I minus half. How would I calculate my pressure gradient? Okay. These are all covered extensively last week, so that's why I'm just quickly summarizing them. This is exactly what I wrote for you. Lambda dp dx in the right minus lambda dp dx at the left interface over delta x is qi. And then I focus on one of them, which is I plus half. It requires lambda at I plus half. And then I need to do the calculation of the derivative, dp dx, at I plus half. At this interface, I need to find out what is my dp dx. What would I do? There is a mistake here, obviously. I hope that everybody notices. Do you see the mistake here? Pi plus half minus pi over delta x. What should it read instead of pi plus half?
Pi plus 1.
Fantastic, exactly. This is pi plus 1. The gradient at the right interface is pi plus 1 minus pi divided by delta x. And remember, this delta x is now the distance between I plus 1 and I cells. This is the distance between these two cells because we are approximating our gradient of pressure with these two cells. So for the first and last cell, where I have to write my gradient between P0 and P left, the distance between the two is half of the delta x. For the last cell too, the distance between last cell and the boundary is half of delta x. That's why this delta x becomes delta x half when I write it for the first and last cell. And the other delta x here is not going to be changed because this is the distance between right and left interfaces of one cell. And even the first and last cell would have the same distance between the right and left, which is delta x. What would I do with lambda average? I said that in the physics course, we are going to cover the concept of upscaling next week, and you're going to be able to just immediately understand what we are doing here. For now, we are just accepting that we are going to do harmonic averaging, largely for the permeability. We are addressing single phase flow. Permeability is the heterogeneous property here. Viscosity stays constant, so I'm not going to make it overcomplicated because in real life we do permeability, harmonic averaging, fluid physics, upwind based. I wouldn't really cover it here. So harmonic averaging of mobility lambda would be for delta x equal would be 2 times one of the lambdas in the one side, the other one, and the summation of them. So if I want to know the mobility average here at this interface, I'll do 2 times of the left one times the right one divided by summation of the two. That's a way to average it. We call it harmonic average. With these, I can now do all my analysis up in here, fit all of them together, and I get these functions at the end. I have some factor here, lambda average divided by delta x squared, lambda average divided by delta x squared times pi minus 1 and the I. So the first one here, we call it transmissibility in the left interface. The second one, transmissibility at the right interface. And if I substitute both back together, I will get the fact that I have discretized my governing equation now finally using finite difference, a staggered grid, with some transmissibility between I and I minus 1 times pi minus pi minus 1, and the transmissibility between I and I plus 1 times the pressure difference between the two. And interesting here is that you are in cell I, you have two velocity, two connectivities. If you think like graph, transmissibility here, the right transmissibility or I plus half, this is transmissibility I minus half. You multiply the transmissibility I minus half with the pressure difference between the I and I minus half, which is the relevant one, and the other one as well. I plus half would be the same. And we know that this transmissibility was based on finite difference. So transmissibility I minus half was lambda harmonic average at I minus half divided by delta x squared. So I'm going to write in code in Python. It means that for cell I, we are going to do transmissibility I, pi minus 1, and transmissibility I plus 1, the difference between the I and I plus 1. This is the interface I, and this is the interface I plus 1. Because if I look into my Python orders, this is cell I, that's the transmissibility of interface I. So this is interface I. This is interface I. This is interface I plus 1 if I do ordering from 0 in my Python code. If it's cell, for example, 1, this is interface 1. If this is cell 2, this becomes interface 2. So transmissibility here is lambda harmonic delta x squared. And if I do for the first and the last cell, what would I get? George, are you with us?
Yes.
Okay, George, what would I write for the first cell transmissibility 0 here?
Lambda divided by delta x squared divided by 2.
Fantastic, thank you very much. Exactly right. Because the distance between right and left interfaces stays delta x. So one of the delta x's stays constant. The other one is half. The distance between the nodes between which I am approximating my derivative operator. And that becomes exactly the transmissibility of the nth interface 2, which is here. The distance of these two is delta x half, but the distance between left and right boundary of cell n minus 1 is again delta x. Multiplication of delta x with delta x half becomes delta x squared divided by 2. And I know that PR here and PL here would be given to me if they are going to be given, if I want to implement a Dirichlet boundary condition. Of course, you have practiced also well modeling as well, but that's only to just make the concept clear. So this is all we did. Finite difference scheme and staggered. We have one last thing to cover before we start the real lecture, is about finite volume approach. And ladies, gentlemen, boys and girls, finite volume is the established method of practice for real reservoir simulators, because they can handle more complex systems, grids, and they are not really so confined like or constrained like finite differences, where you have really structured box reservoirs or grid blocks. Finite difference was the first approach to do the reservoir simulation, especially when we had only structured block way of looking at the system. Finite volume approaches allowed for a lot more flexibilities to be considered in a simulator. Today, most of the reservoir simulators for the flow part and transport, if not all, are based on finite volume method. Or still, maybe if the reservoir simulator is really confined to or constrained to only solve or handle block grid shapes of like this, it might be that it's finite difference, like Eclipse might be still finite difference based. Okay, what's the concept here? The philosophy of finite volume approach is that divergence of your mass balance equation, which is divergence of minus lambda grad P, will be, you will apply an integration over control volumes with your equation, which is Q dV. So you had divergence lambda grad B minus lambda grad B equals Q. You would apply integral over control volumes there, which means, for example, you have this domain and that's your control volume, like omega. So you would apply a control volume integration here. Then you do one thing, a divergence theory like this, or it might be Gauss or divergence, I mix the two. The divergence of fluxes over the control volume will be replaced by, at the boundary, you would do the flux calculation dot n d, let's say, area. That becomes integral Q dV. Finite volume schemes say you want to know divergence of your fluxes, net outgoing fluxes. Net outgoing or outgoing flux minus incoming flux, or out and in, is actually the concept of interface. So instead of integrating over your volume, go and find your influx and outflux. So integrate the influx and outflux at the boundaries. And if I do so, I have minus lambda grad P dot n. N is outward unit vector. It is positive when it is outward. It is negative when it is inward. For this configuration that I'm showing here, I have a flux like this and I have a flux like that. Then I'm going to write my 1D Cartesian system would allow me to use this finite volume approach and write it as minus lambda grad P at right interface, which is I plus half, minus lambda grad P at the left interface, because negative comes here because n becomes negative. N is positive when it is outgoing. Now here you are having incoming flux. So outflux minus influx is equal to Q times volume, delta area times delta x. This is delta area, and the distance is delta x. Now, you can bring delta x below here to put it in the denominator. It would be exactly like finite difference. This is what we did with finite difference. It seems as if we are multiplying everything that we just did by delta volume. And that's true because we are working with simple grids, with structured grids. And then I need to approximate what is my minus lambda grad P at I plus 1, at I plus half, and this is I minus half, and this is exactly what we have done already. This is harmonic I plus half. Delta P at I plus half will be Pi plus 1 minus Pi over delta x. The other one becomes also minus lambda harmonic I minus half times Pi minus Pi minus 1 over delta x. That is equal to Q delta area delta x. If you do all these mathematics, my friends, you would get, this is the nicely written, the same thing that I just said to you. Divergence of this becomes the surface integral. And then if you do the mathematics, you will finally get the same thing that we have done already so far. I am just showing this slide because it will be captured in the record and you can pause it and look into it. And I'm going to be back with my handwriting, which is more beautiful and more comprehensive in my view. Okay, this is nothing that I am really proud of myself. It's just that it's just the fact that it looks a lot better than time. Okay. So in here, when I finally write everything, I get the fact that I have lambda harmonic I plus half over delta x will be multiplied by Pi minus Pi plus 1, because of this negative sign here will be multiplied by this factor, will reverse the order. Then I have plus lambda I minus half over delta x times pi minus pi minus 1. That becomes q delta area delta x. Now, if you bring delta x down here, I'm sorry, there will be area. I missed it. Oh, it's great that I noticed. I have delta area that I didn't consider. So there will be delta area multiplied by them too, because the derivative, the integration is delta area. So I'm going to have also some delta area here and delta area here. So I'm going to have lambda times delta area. So if you divide both parts by delta area times delta x, you will get exactly the same formula as you would have got from your finite difference scheme. Your right-hand side is multiplied by delta area delta x. Left is delta area divided by delta x. Delta areas get out. The delta x in the right-hand side can come in the denominator of left-hand side. You will get lambda divided by delta x squared, exactly what we had before. So for Cartesian rectangular structured grids, the two approaches, finite difference staggered and finite volume, would be the same. Because again, delta areas are the same, and you can easily, delta x's are the same. But if you have the complex geometries, you couldn't easily divide it by delta area delta x, because geometries would be really complicated. That's why the two methods would be different if you have complex grids. So with that, I'd like to just have this recorded for a few seconds that you can also see it here. You see that delta area is not missed here. Lambda is here. So you would do that calculation. At the end of the day, what you will get is this. Your transmissibility is lambda harmonic delta area over delta x. For the first and last cells would be half in the delta x part. But your equation is very interesting, that you get the same equation as you had before. It seems as if you have multiplied left-hand side and right-hand side by delta x times delta area. That's the difference. Here you have delta area, and you don't have power 2 in the denominator, because imagine you have multiplied that. So as a summary, finite volume would give us the same formula to discretize, but transmissibilities are delta area over delta x times harmonic averaging, and your source term in the right-hand side needs to be multiplied by delta volume. Finite difference would give you the same q at the end in the right, but your transmissibilities wouldn't be delta x squared, and there is no delta area here. This is a mistake. It's lambda harmonic divided by delta x squared. So you use either of them. I think I asked your TA to actually cover the finite volume in your practical session. And I hope that you have done that one as well. But if you have done finite difference, it's absolutely no problem. Whatever you have done, that would be fine. And then, this is again wrong. If the P left is known, we know that P left times transmissibility left should go to the right-hand side, because it's a known factor. If P right is also known, Tn times the P right is also known for us. We send it to the right-hand side. We also could have no flux here. We could have no flux boundary and instead have source term, like Wells here. We have done that practice as well. It might be that your TA re-records himself or just releases the record that you had last time with him as well, to actually show you the implementation part of these sort of things. Usually reservoirs in the subsurface formations are mainly like these, and there are no flow boundary conditions usually with them, and the only thing that we have usually is about production and injection wells. So we usually do well modeling mainly. And you did the code. I'm not going to go through the code development that you did last time. You have input parameters like the size of your reservoir, number of grid cells. You calculate transmissibility. With them, you can construct your linear system. And that would allow you solve your linear system for pressure and find your results. One very last point to cover everything we have done last time is that in Python, when you want to construct your linear system, like Ti times this is what we just got in our discrete system. You have a linear system A, P equals Q. Your vector of unknowns are P0 all the way to Pn minus 1. Same for right-hand side, Q0 to Qn minus 1. All rows here would represent one of these equations that you want to solve. So this is for cell 0 all the way to cell n minus 1. And whatever value you put in these entries here would actually be multiplied by its corresponding pressure. Like this would be multiplied by Pi, this would be multiplied by Pi minus 1, and this would be multiplied by Pi plus 1. And so we look into our equation for cell I and find out what are the multipliers. For cell I, this is exactly for cell I, and these are the multipliers of the pressure. For cell I, what's the multiplier of what should be multiplied with Pi minus 1?
Minus Ti.
Absolutely, this is minus Ti. What should be multiplied by Pi plus 1? Minus Ti plus 1. And the summation of the two will come to the diagonal, which is going to be multiplied by Pi. That's why I'm going to get a 3 diagonal matrix for all the cells when I write it for all the cells. Yeah. And one last point is that this is exactly what I just said. For the last and first cell, we know that T0 times P left and P right are known. So this times P right is known. So the multiplication would go to the right-hand side. And here we have only the dependency that should be multiplied by n minus 2, pressure of n minus 2, and some factor to be multiplied by Pn minus 1. Because I have n minus 1, I have n minus 2, and n minus 1 only. There is no other pressure. So there will be 2 entries here for the first one as well. And I can then solve this with Python. Instead of P left and P right, I might have wells, and this is what has been covered already in your practical session. This is a Pieceman well, which says the Q, source term of well, is modeled by productivity index of the well, mobility at the cell of injection or production, and pressure difference between well and the reservoir pressure. And instead of now putting this P left and P right known at the boundaries, I know that I am injecting with wells. So my discrete system for the first cell and the last cell similarly would have only a connection of flux in the right, which is this, transmissibility at cell 1, P0 and P1. There is no flux here, so there is no flux coming, so there is no connectivity there. With the last cell as well, I have flux between n minus 1 and n minus 2. So I am considering that in the last cell, this is Pn minus 1, Pn minus 2. And the transmissibility is here, which is for n minus 1, obviously. This is n minus 1 interface, so that is transmissibility n minus 1. And there is no flux to get out because there's no flux, but I'm going to use my well, the second well, which is P well 1, and the difference with that with the pressure of n minus 1, and then I'm going to multiply it by the productivity index of that well and the mobility at that production cell. This is what you have already practiced in the practical session last week, some references. We call it Pieceman well modeling, by the way, although Pieceman may not be the very first one who did this study, but it's being known as Pieceman well modeling. With those, you did the Python code development. In the practical session, you can set your permeability values and then do these all analysis and find out what the pressure distribution is. We are going to do this practice later in this class as well. And by that, I have covered whatever we have covered so far. And I would like to give you a good break and then continue with the material of this lecture and finish modeling and simulation of flow or pressure problem with incompressible fluid physics. So I hope whatever I reviewed, although it took me about an hour, was useful to go through the entire course now with this record so that it can be hopefully watched again if you are interested to go through some part of them. Let me pause. Okay, so welcome back. So what I'm going to do now is to continue with the lecture and finish it in the next half an hour or so, and then do some practice with the code that you have already developed. My code may look a little bit different, but it's actually conceptually doing the same thing. Okay. The first thing that we would need to know with any discrete system is what we did right. How could we check if what we have done is correct? And how could we check some important characteristics of any discrete system? The first conceptual question here is your discrete equation consistent? And then what's the order of approximation? How accurate is your method? And the convergence and the stability and other aspects come as well. Let's do one by one. Address consistency and order of approximation, and see the discrete system either with finite difference or finite volume, does not matter. With the equation that we obtained, is it consistent? And if so, how accurate it is? And what's the order of approximation? So let's do one step by step, one by one. And I'm going to explain to you, of course, what they mean as well. Imagine we consider the finite difference scheme. So I'm going to just flip through the slides up to here. That was the discrete system that we obtained. Transmissibilities at the left and right interfaces, pressure differences is equal Q. That's the discrete representation of the same equation in continuum word, where you have ddx p function. In computer word, we have pi. We don't have p. It's not analog. It's discrete. So it will be pi minus 1, pi plus 1, and even transmissibilities or factors are all at the interfaces or at the points. They're all discrete. So we are asking a question: is this consistent, and is how accurate it is? Consistency means, are the two equations practically the same? Which means your discrete system is a discrete representation of your continuum equation. But it lives in machine language. It stays in the computer program. So let's do some rearrangement. I multiply ti minus 1 with pi minus 1, bring it here. I multiply my ti plus half with this and bring it here. And there will be 2 multiplication of transmissibilities with the pi. If my lambda is constant, imagine my lambda is 1, constant. It doesn't really matter. So I don't want to include heterogeneity in my studies. I want to have homogeneous system. My t will be equal at I minus half, I plus half. So I can factorize my t. 1 minus 1 will be here. Since I have 2 of these, plus 2 will come here, and minus 1 will come here too. T is constant, I could factorize it. Imagine t is 1, then this term will be minus 1, this would be plus 2, and this would be minus 1. This system here is a discrete representation of d2p dx2. In a way, second derivative of pressure is being approximated by this function, this discrete form in our numerical scheme. Since lambda is constant, I can bring it outside the derivative operator, and that's why it is like that. And that's exactly the corresponding factor here. Now, my question is this. My question is, how accurate is this approximation? And is it a consistent approximation? How could I know this? The whole key idea to this question will come with Taylor series. Taylor series allow me understand, given pi, what would be the approximation of these derivatives in discrete points, starting from pi, moving to pi plus 1, and moving backward to pi minus 1. Okay, so let's do this. What would a Taylor series look like? Pressure at any point xi plus delta x forward. That would be the pressure of xi plus 1. This is the pressure I plus 1. This is the next pressure, which is pressure at xi plus delta x. Delta x forward is pressure at xi plus the delta x derivative of pressure, half of delta x squared second derivative, and so on. That's the approximation of Taylor series. Starting with a function of x, this is p. I have my function. I want to know if I know the solution at a given xi, delta x forward, the function will have this value, that's p at xi, and I want to know what is the pressure at xi plus delta x, which is actually pi plus 1. And I can start from this point, then add the linear part, which is this, then add the second derivative, and third, fourth, depending on the order of approximation, to make myself reach to this point. That's pi plus 1. So knowing pi, what would be pi plus 1? So, okay, knowing this, what would be pi plus 1 with Taylor series? We should do that the same thing with pi minus 1. Pi minus 1 is located at xi minus or plus minus delta x, right? Pi minus 1 is here, which is at xi minus delta x. So cell I is located here, plus delta x, you would reach to I plus 1, minus delta x, you would reach to I minus 1. Now, if you do that with minus delta x, this term would become minus delta x. Would this term become minus delta x squared? No, because minus 1 to the power 2 will be 1. This becomes minus delta x to the power 3. This, to the power 4, wouldn't. So I'll do that here. This is p at x minus xi minus delta x. Would we pay xi minus delta x? Here, you stay positive because it's to the power 2. Here becomes negative. Here becomes positive, and so on. Now, what do I need to have? I want to do one thing. I want to know what would be minus pi minus 1 plus 2pi minus pi plus 1, right? And that's an approximation of minus d2p dx2, right? So that would be the approximation of the minus part. So let's do that. I have to do what? Minus pi minus 1 plus 2pi minus pi plus 1 is what? Is I have to do this. To make it easy, I have to do this. I have to do 2pi minus summation of I minus 1 and I. This is the same, right? I just keep the positive one. The two negative ones, I just sum them, subtract it from this. Which means I need to add these two terms together. And I have them up here. I have them up here. What would happen if I sum these two equations together? The pressure at xi plus delta x plus the pressure at xi minus delta x. What would be the summation?
Delta Q gets eliminated.
I have absolutely. I have two of these pxi's plus delta x times dp dx and minus delta x times dp dx will cancel each other when I sum the two. One is positive, the other is negative. Here, they don't cancel each other. So I will keep it. 2 times of that would be equal plus delta x square d2p dx2 at xi. Power 3 would cancel each other because they are exactly the same with negative sign of each other. Power 4 stays. So it will be plus delta x to the power 4 divided by 12 of d4p dx4 at xi. And plus all other terms, all higher order terms. What do I want? I want 2pi minus the summation. This is 2pi and this is the summation. So let's arrange. If I keep 2pi, so I come with this. If I keep 2pi, pi and pxi are the same, by the way, right? Pi plus 1 is the same as this gentleman here. This is pi plus 1. This is pi minus 1. And this is pi. 2pi, and now I bring these two terms to the right-hand side. So it becomes negative. 2pi minus pi plus 1 and pi minus 1 will be equal. I'm going to send all these terms to the left-hand side. Minus delta x square d2p dx2 minus delta x to the power 4, 12 d4p dx4 and plus all other terms. Is this clear so far? I just summed the two. Found this formula, and then I am rearranging. I'm bringing the left-hand side to the right-hand side, and I'm taking all these other terms to the left-hand side. So I get the formula I want, because this is the formula I want. Or this one. Now I am going to write it more nicer here, because I have delta x square here, right? I can divide left-hand side and right-hand side by delta x square. So I have delta x square now here. This cancels out. 4 here will be 2. So I divided both parts of the equal sign by delta x square. So what would I get? I would get what I am going to show you here neatly. I would get my approximation of minus pi plus 1 plus 2pi minus pi minus 1 over the delta x2 is minus second derivative of pressure with some extra terms. So this is exactly what I wanted to know. How accurate was this approximation? My discrete formula is an approximation of the continuum second derivative function with some error. Because I am not including this part in my program, in my code, right? I would assume in my code that the second derivative is precisely this one. So my error of approximation or approximation, my error is what? My error is minus delta x2 over 12 d4 p dx4 and some other higher order terms. So the dominant power of the error is power 2. So my error is in the order of delta x2. I am approximating with the order of approximation, with the magnitude, with the scale of delta x squared. I am delta x squared accurate. What does it mean if you want to make feeling about? If you refine your grid cells, instead of 10 grid cells, you use 20, your delta x will be half, right? Because you have now more grid cells in your reservoir. If you make your delta x half, what would be the accuracy? Would it become twice more or 4 times more?
4 times.
Absolutely. So this says that your approximation of of second derivative of pressure to be this is second order accurate, which means if delta x, the second delta x or the delta x2 is, let's say, half of your delta x of simulation 1, then your accuracy or your error will be a quarter of the error of your simulation 1. Because the error or approximation that you have is a function of delta x to the power 2.
Sorry, Hadi.
Yes.
I don't really understand why the error is second order instead of third order.
Because of delta x, because we also neglect this one too. We neglect this one and this one. Okay? And since delta x is less than 1, to the power 2 is bigger than to the power 3, than to the power 4, than to the power 5. So the leading error is delta x to the power 2. Imagine delta x is 0.1, okay? So you have a reservoir of 1, made 10 grid cells there. What would be delta x to the power 2?
Yeah, it would be higher than to the power 3.
Exactly. If delta x is 0.1, delta x would be 10 to power minus 2 delta x.
Yeah, 1 divided by 100 instead of 1 divided by 1,000.
Exactly. So the leading factor of your error is 10 minus 2. So it's bigger. So it's 1% error. Delta x3 would be the other decimal. Delta x4 will be the other decimal. So the leading factor is delta x. By the way, so that's why we actually do this in here. Okay? Is that now?
Thank you.
Of course. So this is order of approximation. My order of approximation is 2 because that's the power of my delta x. Order of approximation is 2, meaning that if I refine my grid by a factor of 2, my error will be smaller by a factor of 4. If I make my delta x divided by 3, my error would be less by a factor of 9. Wow. Is this a consistent discretization? Order of approximation we found. Yes, it is. Why? What does consistency mean? Consistency means something extremely important, extremely simple. Consistency means if you reduce your delta x, make it tend to 0, would your error also go to 0? if delta x becomes a smaller, 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 so delta x is smaller, 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 you do mesh refinement, would your error also decrease all the way to disappear? Is this the case here? Yes, it is. So it is consistent. Consistency means the continuum word and discrete word become the same spaces if delta x and delta t become 0. Consistency means that the only difference between your continuum word and your discrete word is about delta x and delta t. Delta, this discretization. You did not add more sources of error. You didn't approximate anything on the physics, anything else. It's only about discretization. And if you make your delta x smaller, 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 the two words get closer to each other. In a way, you have continuum word, you have discrete word, which is far from the continuum word because of delta x error, because of those error terms that I have shown there. But if you make a delta x smaller, 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 the error will decrease, 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 all the way that it becomes the same as the continuum word. That's consistency. Consistency means the two systems become equal if delta x goes to 0. Order of approximation is how fast it goes to become the same as the other space. Is it second order? Is it third order? Is it fourth order? What or how fast it becomes 0? That's order of approximation. Good. So the second derivative of pressure is approximated by this formula in a second order accurate in a space. That's what we just covered. And also some text that when you have, the transmissibility is equal, you have this continuum word, the exact solution and the approximate solution are now delta x square different. This is what we just did. And the system is said to be consistent and has consistency of order of alpha if the truncation error, the error that we just described, is in the order of delta x to the power alpha. And alpha should be more than 1. Because when you want to decrease your delta x, you want the error to go smaller, smaller, smaller. Now, this is second order approximation. You could do higher order approximations if you want. You can make it fourth order. You can make it fifth order, sixth order. But all would require more points, it would be a lot more expensive. And since pressure equation is already an expensive part of reservoir simulators, and typically understanding the right transmissibility is a lot more important and uncertain, we aren't really fancy of higher than second order approximation in real life business. Because it's simply just imagine you have 50% inaccurate estimation of your permeability. Now you want to go make your second order approximation, fourth order approximation, as if you have a number like 2.506, and now you know that it may be 2 or it may be 10. And then you go and do a lot of computational effort to go and change the digit here instead of 8 to look 9. We don't know if it is 2 or 10. Why would you, add a lot more effort to just increase accuracy in 5th digit, for example? So that's why we rather have accurate, reliable, robust simulator that would then allow us to do multiple realizations quickly and have an estimation of where we stand in terms of our uncertainty, rather than spending too much effort and make it higher than this, higher accurate than this. Okay. So that is all that was needed for this order of approximation. One last graph to show you is that your error in your first grid cell is proportional to delta x1 to the power m, which is 2 here in this practice. The second grid cell is delta x2, so you would get second error. If you make it half of delta x1, your error would be fourth of error 1. If you divide the two errors, that would be proportional to the delta x1 to the delta x2 to the power m. So if you make your grid cell half, your error would be 4 times less if m is 2. Now you can apply logarithm. We know that ln A over B is ln A minus ln B. So if you apply logarithm to epsilon 1 to epsilon 2, it will be ln E1 minus ln E2. That's what you see here in the denominator. Ln of, so that's one thing. Ln of delta x1 to the delta x2 to the power m is m times ln delta x1 delta x2, and that will be m times ln delta x1 minus ln delta x2. Again, A divided by B, and that's exactly the denominator here. So in this way, you can find the order of approximation this way. So if you see a lot of scientific papers, they plot in the horizontal axis logarithmically their delta x. So that's ln delta x. And in the vertical axis, they plot ln of error, which is logarithmic scale of the error. So they plot it logarithmically. That's for delta x is 0.1. Here, oops, sorry. Here, for example, this is for that delta x. This is for delta x. This is for this delta x. So this is 0.001. This is 2 times 0.001, 3, 4. So you can do this logarithmically. And then they plot these error, and the line that connects these all together will have the slope of m. You will see the slope will be m. So that, and if you have higher order approximations, your slope will be like this. Your slope will be faster. If you have lower order approximations, your slope would be smaller. So that's the order of approximation, which is the slope of this line. That's a practical way to plot it, and many scientific papers actually use this way. They call it grid refinement or refinement, grid refinement. Each grid cell, you would have some sort of error. You calculate the difference between your result and analytical result. Exact solution. And obviously you can do that for the cases you have analytical solution for. You cannot calculate your error without knowing your exact solution, right? So you do that for very simplistic cases where you know what the mathematical solution should look like. And then you test this. So that would be it. I think we have done, now we are done with the order of approximation. And the last thing I need to cover before we do a little bit of code practice is how do we extend whatever we have done to 2-dimension. So it's going to be very easy, 10 minutes speaking, and then I'm going to do some code practical with you, and that's all. So whatever we have covered so far was about 1D systems. Okay. So how would I go forward to multi-dimensional systems? How would I do 2D? Because 2D would be also very practical, very interesting. So many of your even master thesis work, if they needed some sort of proof of concept implementation, a 2D simple system could be also enough in many cases. So it allows us to understand the multidimensionality in the streamlines, in the velocity field, in the pressure field, and a lot more involved system solving as well. So the main part here is how are we ordering as our unknowns? How do we store them and access them rightly? That's all about multidimensional systems. It's usually a problem of data structure mainly. So that's a 2D system. Instead of having only one line, we are now going to have stack of 1D reservoirs on top of each other. And flow can happen anywhere. Flow can be multidimensional. And this is really nice. So the concept stays exactly the same as 1D flow. Now, instead of having only left and right neighbor, only left and right neighbor, east and west neighbor, we have now two more neighbors here too, with which we exchange flux, south and north. So we have east, south, north, west, and that's it. And so if I solve this problem, for example, for a given pressure here and no flow everywhere else in my system, with this heterogeneous reservoir, that's the pressure distribution that I would observe. And looking at this pressure, you can understand a lot of physics already. You see, there are places where the gradient of pressure is small. There are places where you have sharp gradient in your pressure. This is sharp gradient. This is slow gradient. This is a slow gradient. You can already have good feeling about your pressure. This is sharp gradient. If you have velocity constant, based on Darcy's law, your pressure gradient times mobility should be constant. If mobility, for example, for single phase flow is permeability divided by viscosity, if permeability is very high, do you need small delta P or high delta P to maintain the flux?
Small.
Small. So wherever you have a small gradient of pressure, it means that you are, here it's very small. This is exactly where you have permeability is red and it should be really high. These places where you have an extreme gradient, sharp contrast in the plot of pressure, if you translate it where it happens, this is a shale formation. This is low perm system. Because you need a lot of pressure gradient to push flow forward from that barrier. It may never even happen. So you may even rather to have your flow to go over this instead of going through this. So usually, you see, by looking at this, you will get a lot of understanding here too. We are going to do the code practice right now so that you will get better understanding of this, of what I just said. Now with this 2D system, what is it going to happen? You are going to practice this tomorrow. So it's going to be repeated again and again, and you're going to fully understand what that means. Excuse me. So I'm going to order my system and store them either row-based or column-based. I go for row-based here. I go for row-based. So I make this to be my cell 0, my cell 1, cell 2, all the way to cell nx minus 1. Then I go to the next cell, which is this, nx, nx plus 1, nx plus 2, which is nx plus 0, all the way to 2. This is nx plus 2. This is nx, 2nx minus 1. Again, I go to 2nx all the way to 3nx minus 1. So I do this way of, this way of ordering, row-based ordering. Now, my main question here is, if you are given cell I and j here, what would be its order? What would be the order of cell I here? This. I know there is a cell I and j in 2D. I want to know what is the index of it. What would be the index of I, this cell? If I is 0, j is 0, I know my index is 0. If I is 0 and 0, index would be 0. If I is 1, j is 0, index will be 1. If I is nx minus 1, j is 0, index will be nx minus 1. Now, what happens if I put I and j generic? what would be the index? Can you think about it a little bit and see what do you think the index would be?
Jn plus I.
One more time.
Jn plus I, maybe.
Who is speaking?
Oh, Ewald.
Ewald. So you said one more time, please.
J times I, J times N plus I believe.
What n? Nx and plus I. This is what you're saying, right? I just wrote it above. Right? Is that right? This is what you just said. So which means that, so I put it up in here to the top right. So Ewald says, if you put 0 and 0, it works. If you put 0, 1 and 0, so for the first row definitely works because J is 0 for the first row and I is exactly the order. Now we go to the next row, we have passed nx minus 1 already. And then we put, for example, let's put, what's the index of this cell that I just painted red?
NX.
Yes, this index is nx. What's the I and j of it? I is 0, j is?
1.
1. So if I put j1 and I 0, would it work? Yes. So that's correct, actually. So the index of cell I and j is precisely j times nx plus I. That's the way we order. You put any I and j, it gives you back the capital I, which is index of cell. Now, how about the left, the east, west, south, and north neighbors? We just need to put their I and j values there, right? The west neighbor is I minus 1 and j. The east neighbor is I plus 1 and j. South neighbor is I and j minus 1. North neighbor is I and j plus 1, right? So we just put these functions there in the same formula that we had. And that's exactly what we are going to do. So I west is cell I minus 1 and j. I east is cell I plus 1 and j. I south is cell I and j minus 1. And I north is I and j plus 1. And with this generic function that I have for any I and j, I'm going to use this generic function and find the index for each of these neighbors. So I put, instead of I put I minus 1 here. Instead of I and j, I put I plus 1 and j here. Instead of I and j, I use I and j minus 1 for this, and I and j plus 1 for this, to find what is the index of it. So capital I west, I east, I south, and I north are my indices. When I stack this 2D problem as 1D stacks of row-based ordering, so I number them this way. I could do the same thing vertically based on column-based ordering. But I have decided row-based ordering here. The science would be, if you do column-based ordering, I and j would replace each other, and instead of nx, you need ny, naturally. And this is all about multidimensional systems. Now that you know how to access your neighbors, you can go and read properties. You can calculate your stuff. It's not just 2 connectivities. Now you have 4 connectivities, like this here. You have the property given to you. This is permeability from geological characterization or geophysical surveys. You are going to be given with one possible realization here. You know that cell I and j, any cell I and j would have 4 neighbors here in this 2D system. It would have 6 neighbors if it was 3D. You would have front and behind as well. And Transmissibility would be for each cell, you would have two types. One is for the X, for the horizontal flow, another would be for the vertical flow. So you would define transmissibility X and transmissibility Y. And this would be transmissibility X would be these interfaces would need transmissibility X. All these interfaces would need transmissibility X. And then you would do also for these interfaces transmissibility Y. So you would do this ordering to find your transmissibility Y. How would you do that? Again, using harmonic averaging, now for lambda X and for lambda Y, and your delta area divided by delta X. But you need to remember the ordering Tx is going to be harmonic average of, for example, transmissibility X for interface I. This is interface I. Interface I is what? Is this? Is the left interface. Is a harmonic average for the mobility between cell I and I west. So that's the transmissibility between I and I west divided by delta X between I and I west times delta area. Now, obviously, I have done a mistake here for transmissibility in Y direction here, in Y direction, you need delta Y, not delta X. Because it's just rotated by 90 degrees. So you would have cell here. This is cell I. This is cell I south. Transmissibility Y for the interface I, vertical interface I, would be harmonic average, delta area, and delta Y, because that's the distance between I and I south. And this is what you are going to practice tomorrow to calculate these transmissibilities. And once you have them, you are going to do what? You are going to translate this function. Now, instead of just knowing Txi and east, which is the I and I plus 1 that we had before, now you're going to have also I and I north as well. So they are going to have not just two velocities, but we are going to have four velocities, four fluxes, because it's not just this and that, also this and this happen as well. So there are four vectors that you need to consider. There is a communication between I and I west, between I and east, between I and south, and between I and north. Another typo here. This is I and I north. By the way, I'm going to send you the slides soon, just after the classes. And that's it. Then we feel that the system, starting from index, this is index, of course, P index, P0, all the way to the last cell. Here, this is the vector of unknowns. All of them is stacked into 1D vector. And for each cell I know that there are not going to be only two transmissibilities, but also I'm going to have the other two, which is between I and not just X direction, but also in Y direction. And I'm going to have I and I east there. And then I'm going to have I and I north here. I and I north here. So this is going to be multiplied by I north. This is going to be multiplied by pressure of east. This is going to be multiplied by west. This is going to be multiplied by south. And sum of all of them would be multiplied with positive sign to the I itself.
Are the indices on the left side of the matrix not missing a letter? Because now they're both dependent on I, but aren't they supposed to be I south and I west?
No. This is I. Well, this is I interface I, because when you start to order it.
Oh, right.
you do only Tx first. So Tx0, Tx1, Tx2, Tx blah, 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 and then Tx this, Tx that. So Tx would have, for I would be the left guy here. This is Tx. Then you again duplicate this. And then this is Ty0, Ty1, Ty2, Tynx minus 1. These are the Ty's. So you would store this in here. For any cell I, the transmissibility xi will be the left, transmissibility yi would be the south. For the other two interfaces, you need to access the other one. And for Ty especially, it's tricky because for Ty, when we want to go this one, it's actually the ordering would be this. So it's gonna go, it's not 1 plus, so that's why I write it east, north, and I itself. But practical tomorrow would make it a lot more clear. And that would be it actually. You are given reservoir geometry, number of wells, boundary conditions, parameters. You would impose your grid resolution, define the permeability at each grid cell, and then form your two-dimensional system now in 1D, all of them are stacked, row-based, and you can solve and simulate and find pressure distributions like this, which are extremely insightful and interesting. Even at this 2D surface, you could do a lot of sensitivity analysis, uncertainty quantification, or even connect it to your outcrop geology or other characterizations that you're going to do. Because this is interesting because you can also change the permeability in your system and see how the pressure would change. You could mimic existence of fracture by taking part of this, for example, grid cells to be extremely high perm, so make permeability extremely high, then it would make a replication of extremely high channel there. Here, the blue means there is a shade formation here. So there are so many things you can play with and understand what's happening. Okay, so that would be all about flow and pressure simulator. We covered the governing equations for incompressible flows. That was mainly minus divergence lambda grad P equals Q. And once we solve for pressure, we can find velocity from Darcy's law to be this. We developed 1D simulator already in our practical class with well modeling, and consistency is now covered, which means if delta X or delta T, they go to 0, your truncation error, your difference between discrete and continuum work would go to 0 too. How fast it goes, it's the order of approximation. Second order, third order, fourth order is order of approximation. 2D simulators can be also developed with the same concept of 1D. The only difficulty here is just to make sure that I and J in physical space would have one-dimensional index associated with them. You're going to practice that tomorrow. And what is left for me, I would like to share my other screen. Stop sharing. And I would like to change the screen that I'm going to share with you so we can practice a little bit with the 1D code that we have developed before and do a little bit of analysis here. So you should see now my Python code. Do you see?
Yes.
Okay, this is very much similar to the code that you have developed. It's not in Jupyter, it's in PyCharm, but it's precisely the same concept. And it's exactly the same code. So I started with length of my reservoir to be 1, number of grid cells to be 20, and this is the grid sizes. And I'm setting the Dirichlet boundary condition in my code. So I'm giving pressure 10 in the left, pressure 0 in the right. For your report, please make sure to put dimensions there. Here I don't put, you put. No wells added for this practice. For X center X's, you have line space between the first cell centroid location, which is half of the delta X, all the way to the end with N grid cells. And the interfaces are between 0 to length of the reservoir L with N+1 interfaces. Mobility is K divided by viscosity. I just call this all mobility is N size vector. harmonic average and transmissibility would be n plus 1. So the good thing is that this is going to be recorded, so you can actually pause the record later on when you watch it, so to see if you want to see any specific thing in here. Now I would like to do this, and I would like all of you please do this in your code, your way of doing. Put mobility equal to 1 for all cells, the way, whatever way that you do all the time. I am doing it with for loop from 0 to n. I set the mobility to the value constant 1. So can you please do that with your code? Can you open your Jupyter code and your Python code, either in Jupyter or PyCharm environment, whatever you have developed, and set the mobility all to be 1?
I think we already did that. We wrote mobility is np dot ones and instead of np dot zeros.
Okay, good.
Job.
So then can you please run your code and see if you get what I get? I am going to run my code. And this is the plot that I get. I have put my pressure on the left boundary to be 10, on the right to be 0. And I see a linear decay of pressure. It's a homogeneous reservoir, 1D, incompressible flow, steady state. And so the left is 10, the right is 0, and I see a pressure dots across my reservoir with the 10 grid cells, no, 20 grid cells that I have. Do you see the same thing here?
Not yet.
Okay, please just take your time, don't worry. So I'm going to rerun again. I'm going to speak now while you are running your code, because I would like to use this time of the record for some explanation of what I am doing in my code for those who haven't been in our practical sessions and are watching this video later. What we are gonna do is that after we are calculating the mobility, we are setting them all to be 1. We start by calculation of the harmonic mobility and transmissibility finally. In our practical sessions, you might have done it differently. That's one way of doing, and I'm sure your codes also work. The first and last harmonic average would be the same as the first and last cell property, because there is no neighbor in the left, very end left and very right end of the reservoir. And in between, mobility for constant delta x. So only if delta x is constant, it can be defined this way. So this is harmonic average mobility when delta x is constant. Okay. And then we calculate transmissibility. We know transmissibility based on finite difference. I am doing it, of course. You might have done it with finite volume, which I would like it a lot more. But now this is finite difference based transmissibility. And you know that for the first and the last interface, the transmissibility would be half of the delta x squared 2. So it will be twice higher at the end. In between, you are going to do mobility harmonic divided by delta x squared. You could plot it and see how things would look like. Then you start filling your AP equal Q matrix. And if your I, cell I, is more than 0, then you have left neighbor. If your I is less than the last one, the index of the last one, you will have the right neighbor too. And so you would add the contribution, and then here you would impose your boundary condition. If it is Dirichlet condition, which is the case, we are going to put the transmissibility 0 to the left, to the right-hand side times PL, and also the last transmissibility to the right-hand side too. And the last part is that I'm going to solve this AP equal Q and plot my pressure. So that's all about this code. So could you run this code for mobility 1 and get the same result as I'm getting?
I got it.
Okay, great. So you could keep yourself unmuted. If you don't have background noise, then it would be convenient to just speak, and it would be fine if all of you speak at the same time too. Okay, this is also, by the way, the plot of transmissibility. Since my grid is the delta x is 1 divided by 20, My transmissibility would be delta x squared would be 400. 1 divided by delta x squared would be 400. I'm going to get 400 everywhere except the first and last interface where I have twice as high because it's delta x squared divided by 2. So that's why transmissibility at the first, 0th, and nth interface would be twice higher than the rest of the reservoir. Okay, and this is the pressure that I see. Now I have one question for you. Let's go to the midpoint of my reservoir. Let's go to the midpoint and change the mobility there to be 1,000 instead of 1. And I have one question for you before you do that. Toon, are you with us? I just want to randomly pick some of you who have not. Okay, Toon. I am going to change my mobility at the center of the reservoir, around center, to be, instead of 1, to be 1,000. Mm-hmm. What would you think would happen in my pressure plot? How would it be different?
I think the pressure would increase.
I am fixing the left and right to be 10 and 0. In between, I have uncertainty because of my data collection. I don't know if the permeability or mobility is 1 or it is 1,000. I have tried it with 1 and I see linear decay from 10 to 0. Now I would like to change that and make it 1,000. That's sensitivity analysis. I'm changing it instead of 1 to become 1,000. How would this linear decay would be affected by this change? Would I see again constant line like this?
That's a good question.
This is exactly why we need
I'm not
this.
really sure.
Yeah, you see, you have a reservoir in which you have permeability 1, 1, 1, 1, 1, 1, 1. All of a sudden, in the middle, you may have fractures there. Your permeability becomes 1,000 times higher, and then it becomes 1, 1, 1, 1, 1. We want to know what would the pressure look like. So let's run this code and see how it would look like. I put the midpoint. Do you see the difference here? Pressure is linearly decaying here. All of a sudden, in between where we put mobility to be 1,000, the slope becomes higher or lower?
Lower.
Lower. It becomes lower speed, and then it goes back with the same speed as before to B0. Why the pressure gradient became lower when we increased the permeability?
You need less pressure to get the same flow.
Exactly, because in 1D systems, divergence of U in compressible systems, divergence U is 0 because there is no source term also here, which means U is constant. ddx of U is constant in 1D incompressible systems. When U is constant, it means it doesn't change. What is U? Based on Darcy's law, U is minus lambda grad P minus lambda dp dx. If lambda is high, dp dx would be low, so the multiplication would be constant. So by looking at this plot, I can tell you that you have put high permeable grid cells in the middle of your reservoir. So when I want to double check your codes or I look into a pressure plot, this is what I understand from it. We don't develop simulators for just the sake of curiosity all the time. We develop them to understand and analyze and do sensitivity analysis. And that's exactly what we do with it. Now let's put it, instead of 1,000, let's see, we have a shale formation there. Oh, that's not so good. So I am going to have 1,000th of permeability instead of 1,000 times more. So I'm going to have 1,000 times lower permeability in the middle of my reservoir. Okay, so Renz, what would you think that would be? Would I see slower slope in between, or I would see sharper slope?
Sharp slope.
Fabulous, absolutely. Let me run it again. See, how big the jump is, because you need huge pressure gradient to make the flow pass through this shale formation. Permeability is so low that you need huge delta P to create constant velocity across your reservoir. Was this clear to everyone? These are the studies I would
yes.
appreciate you include in your reports about sensitivity to the parameters. This is when you have high perm, low perm, heterogeneous contrast. I'm gonna be back to you, Salim. I heard your voice. I'll be back to you. But let's do this. Let me even comment this out and hope that this would work with this random function. That's the random function. You see, random function is having the blend. It's a milkshake of all these high flow rate, low flow rate. So you have high drop, low drop, high drop, low drop, high drop, low drop, high. So it's, you can already guess what the permeability distribution is. When you have low pressure drop, then you have high permeability. Here, permeability becomes lower, then it becomes higher, then it becomes lower, keeps almost the same. Again, a little bit higher, less permeable, higher permeable, higher, and this and that. So you understand what's the permeability distribution from the looking at the pressure plot. And I'm gonna avoid random because random has too much in it. And I'm gonna be back to the homogeneous plot once more. That's my homogeneous linear plot. And now I am going to create a barrier here with 1,000 times less permeable. And whew, this is what I see. I can make it 100 times less permeable instead of 1,000 times. So you're gonna see that the drop is not as significant as this one. See, it's a little bit less sharper. And if I even make it 0.1, that's what I see. See, it's a little bit. And then if I make it 1, which would be equal to all other grid cells, you would see linear plots. And I can continue, make it 10. It should be slower in here. See, it becomes a little bit lower. Now I make it, instead of 10, I make it 10,000. So extremely fractured. See, it becomes horizontal more. I can make it even 1 million or maybe even 10 million. This is 10 million times higher permeable. It becomes even further. You can't hardly just actually see that high increase here. See, it is trying to change itself. So that's all about sensitivity analysis with respect to permeability distribution in your reservoir. So any questions?
Yeah, I had a question.
Please.
I don't get how you get to the homogeneous graph because I changed my mobility, but I have a straight line.
It depends on your pressure difference. What pressure do you set in the left and right? I am putting 10 and 0. I'm setting P left to be 10, P right to be 0.
I think, Salima, your problem is that you only ran the first cell. You should get the other graph in the second cell.
Okay.
So that's my homogeneous system where I set the mobility also equal to every other cell, and that's what you would get. Yeah.
Yeah, and make sure you plot pressure, not lambda.
Exactly. These are also, this is the homogeneous curve. This is when you have extreme contrast, heterogeneous. You have a smaller contrast in the heterogeneity. This is higher perm because the slope becomes lower and so on. So that was it, everyone. That was the flow solver, 1D and 2D, and some practice with the code. I would be delighted to see your report that you change purposefully part of your domain, either 1D or 2D, and then interpret what you observe as a result of this change of parameter. because it's quite common in geosciences to have uncertainties with respect to the data population and estimation of the permeability in the field. Okay.
But this is for forward and inverse modeling practical, right? Not for the physics practical.
Yes, this is for the only forward and
Yeah.
inverse modeling, of course, yes. So I'm going to